so there are two reasons to study spinners in this class, in the context of GR in general. One is because there are fermions in the world, and fermions transform in spinor representations. And if we want to understand how to do physics with fermions, then we better understand how to do spinners with them relatively. It is not as simple as just sticking a spinor index everywhere we previously had a vector index. That won't work. We'll see why. The second reason specific to 4 dimensions. So in 4 dimensions, the Lorentz group is SO3, and thinking about SO13 in terms of spinners turns out to be a very smart thing to do, even if you couldn't care less about fermions. So there are reasons to use spinners in GR, completely separate from the fact that we have fermions in the world. And in fact, people who do hard GR calculations often do it in spinor language instead of tensor language, just because there are dramatic simplifications by using spinor methods in 4 dimensions. Now, that story is very specific to SR13. There are analogous stories to a certain extent in other dimensions, but they're different. The tricks are dimension dependent. I want to talk about both of these purposes, both of these applications. I'm going to start with general dimensions and physics of spinor fields, which is related to fermions and quantum mechanics. We're just doing classical mechanics, so we're about fermions. We'll talk about spinor fields, and how to couple them to curved spacetime, and then we'll specialize the 4 dimensions and talk about the spinor tricks that we can use there and how that will greatly simplify one's life in GR. So, unfortunate fact about spinners, which there are no good references, at least none that talk about it the way I want to talk about it. The close is a book by Friedman and Van Proyen on supergravity. I'm going to try to follow the Friedman and Van Proyen conventions wherever possible, but they don't talk about, they do this, they pretty much don't do this. So they talk about Dirac spinners, but essentially don't use Weyl spinners in this book. And this is all about Weyl spinners. So at some point we're going to have to depart from Friedman, but not today. Some other good references. So Green, Schwartz, and Witten's book on superstrings, chapter 12, is a very nicely written introduction to some of this topic. It's called Spinners and General Relativity. It's worth a read. For 2 component purposes, that is basically for part 2 here, there's a review online that I like, which you can find by searching Google for DHM spinners V5, and that'll take you to the webpage that has the review. This review is also posted on arXiv, but the arXiv version uses the wrong metric signature, or the opposite metric signature compared to ours. But fortunately, people who wrote this review thought it would be a good idea to include some special compilation flags in their LaTeX. And you can recompile the LaTeX with the other metric signature. It's awesome. and that'll give you this file. So this will give you our metric signature. Another good source is Chandrasekhar's I can't remember what it's called. I think it's called the Mathematics of Black Holes. A really good reference to not read is Wall. Okay, so go for it if you want, especially maybe after we cover it. But it's really just sort of awful. It also specializes. Nice. So some of these books, some of these sources specialize to two-component spinners right off the bat. So they're good for that purpose, but not where we want to start. Before we get into the meat of this, I want to let you know that there's a talk today at 3 p.m. in PSP 120. So this is the second lecture of the beta lectures that are going on this week. And it's on roughly on anomalies in cosmology, various experimental anomalies, and trying to synthesize some of that. So I think this will be a really interesting talk. I encourage everyone to go, so that's right after lecture today. Okay, without further ado. I'm assuming people have seen fermions before, because everybody raised their hand when I asked if you had taken quantum field theory. So in this first, is that accurate? People have seen fermions before? It's too late now, anyway. Okay, so I'm going to start with an introduction to why we need spinners and what are spinners, which is maybe not the best introduction if you haven't seen this before, but I'll try to say some things that are new to you if you've only seen this once or twice. So the question I want to start with is, what is a field? I want to revisit this question and keep careful track of some global issues, and in particular the distinction between symmetry algebras and symmetry groups, because this is where spinners shine. So the restricted Lorentz group is called various things by various authors, but I'll call it SO plus 1 minus 1. And quickly review the O orthogonal means it satisfies this equation. The S means the determinant is +1, and the plus means that it preserves orientation in time. So these are the generalized rotations that preserve orientation in both space and time. We can parameterize them by a set of real numbers, lambda, by writing. So these are just matrices. These are d by d matrices. We can parameterize them in terms of d over 2 times d minus 1 real numbers by exponentiating the generators of the algebra. So T here is the generator of the algebra SO1 d minus 1. As I'm writing on the board, it's hard to tell that I've given this lowercase SO. So if you look in the book, it's clear. Maybe I'll put a little squiggle under it. Sometimes people write these with a funny font or make them lowercase. case. I want to be careful about the distinction between the group and the algebra. This is something that often we gloss over in physics. Actually, there's a very good reason that we gloss over this in physics. And the main point I want to get across in this intro is basically why we gloss over that distinction. I don't want to just gloss over it, I want to gloss over it for a good reason. So these generators are themselves matrices given explicitly by just the product of delta functions, or since we have a time component, product of eta functions, eta mu rho, eta mu sigma, minus eta mu sigma, eta rho mu. So this group is connected. Connected meaning that every element of the group is can be continuously deformed to the identity. It's connected just because I put the word restricted here. If we had O1 d minus 1, that would have various components, which are basically these things, but without the sign constraints. So it's connected. We've defined it as the connected part of the orthogonal group. But not simply connected. That is, there are non-contractible curves. You can think of this group itself as a manifold, and there are non-contractible cycles on that manifold. So here's one, the only one, in fact. The curve gamma, which is a rotation by phi, and phi runs from 0 to 2 pi. Is a closed loop that starts and ends at the identity element of this group, but cannot be continuously deformed to the identity. So is not contractible. How do we picture this? We can think of this. You can think of this curve as the procedure that says rotate an object by 2 pi. Okay, so that's the whole curve, right? It's not the rotation at the end. It's the whole procedure of rotating it. And the procedure of rotating an object by 2 pi cannot be continuously changed to the procedure where you do nothing. There's just no way of doing that. I think this will make a little more sense when I explain 4 pi rotations. But you can try as you might to come up with a way of continuously deforming that procedure to the procedure that says not to do anything, and you're going to fail. So far? Yeah.
Is the values that you've given for t, is that in a certain representation, or was that just definition?
Well, here I meant the defining matrix representation. So I'm literally taking these t's to be matrices whose components are this.
And you haven't chosen a representation? No.
I have chosen a representation. So this is what is this one called? The fundamental representation. Because I've picked the matrices. Yeah. The matrices are these are their components. So this is the fundamental representation. And I was using this particular representation of the algebra to define them. This is the defining representations of the group, where these lambdas literally mean matrices. I mean, so SO, these are orthogonal matrices, D by D matrices. And these lambdas here are D by D matrices. This is not some abstract group theory object. This is a D by D matrix. Yeah.
When you say it's the only one, you mean all others are connected to this? All other non.
This is the only non-trivial one. That's right. Yeah. Okay. So this is the restricted Lorentz. The Poincare group, or the restricted Poincare group, is just Same thing. Together with translations. So I'm not going to define this notation because you all know what translations means. The I is for inhomogeneous. So the translations act inhomogeneously on the coordinate x. X under an iso transformation, Poincare transformation, parameterized by lambda and a, goes to x prime, we shall denote as lambda inverse x minus a. Some people use the inverse convention. So some people define x prime to be lambda x plus a. But I'm going to follow Friedman wherever possible, and Friedman defines things this way, so this is what we're stuck with. Acting on a field, the transformation says that, so under a Poincare transformation parameterized by lambda and a, psi of x goes to psi prime of x, which is some operator parameterized by lambda and a, acting on psi of x. Now, I want to allow this field to transform in some, or to have indices that transform under Lorentz transformations. So this is, I'm not writing the indices, but this is secretly psi I, and this is secretly d I j, so that it can act on the field indices. But D acts on both the field indices and on space-time. So d lambda a is e to the minus lambda rho sigma x bracket rho d sigma minus a half lambda rho sigma m rho sigma times e to the a mu d mu. So where's everything here? So this is a differential operator that obeys the SO algebra. This is acting on the coordinate. This is giving you the translation. And this thing here is the part that we're going to be most interested in. So M rho sigma is a matrix, Ij, acting on the indices of the field, psi j. So this transformation in total does three things. It implements the two transformations on the coordinate, and also does a transformation on the field. The differential operators are chosen in such a way that they just shift the argument of the, sorry, I missed the M. Lambda psi lambda x plus a. So they just shift the argument. M here is the part that acts on the field indices. So M is e to the minus a half lambda rho sigma, M rho sigma.
Question? I think the way you defined it is there should be a bracket around x plus a, unless you want to put e to the a mu d mu on the left hand side.
Let's check. Okay, so equivalently, if I did it correctly, then this should be the same as saying that psi prime of x prime is equal to m of lambda psi of x. Okay, to note that up here, I was just transforming the field and not its, I was transforming this function, but not its argument. What should happen is that psi prime of x prime should just be act on the indices, and then evaluate the same point x. So this is one version of this of the tensor transformation laws that we started with in GR, where you take a tensor and then you get t prime with the prime indices at x prime, and then m in that context is just the usual tensor transformation. So this should agree with that if I did my minus a correctly. So let's check the scalar. So for a scalar, m is just 1, there are no indices. So phi prime of x should be phi of lambda x plus a. And then phi prime of x prime is phi of lambda inverse x minus a plus a. Which is phi of x, so I think I did it right.
So I just meant that one seems to translate first, and then act, the operator D seems to translate first and then act with the Lorentz operator.
Oh, I see. You're saying I just should put that over there?
Yeah.
Okay, that's probably right. Okay, so this is just our usual transformation law for fields, but I'm writing things a little bit different. Does this make sense? The transformation law for scalars that we introduced months ago was just this one, phi prime of x prime is equal to phi of x. This is the same. Okay, so now we're trying to answer the question, what is a field? Well, we just pretty much defined how things transform. So the question we want to ask is, what fields should we consider? i.e., what are the allowed transformations m of lambda under the Lorentz group? So that's a physics question, not a math question. And it's a question that needs to be answered by experiment. Experiment says that we're secretly doing quantum field theory in the classical limit. And that almost is enough to justify the following statement, which is that fields on Minkowski transform in finite dimensional projective reps of SO plus on D minus 1. I'm going to unpack this statement. First of all, let me define the word projective. Projective means up to a phase. That is, m of lambda 1, m of lambda 2 is equal to m lambda 1 lambda 2 times a phase. Or times, that phase might be trivial, but it's potentially times a phase. So when I say projective reps, I mean projective reps or truly projective reps or just ordinary reps. So that is that the fields almost have to obey the Lorentz group structure, but not quite. They only have to obey the Lorentz group structure up to a sum. So where does this postulate come from? Well, it almost follows from quantum field theory plus an old theorem of Wigner. So the theorem of Wigner about quantum mechanics in general says that symmetries have to be realized as unitary or anti-unitary operators acting on Hilbert space. Sorry, the states have to transform. Right, so symmetries have to be realized as unitary or anti-unitary operators, and then states have to transform into projective reps of those symmetries. And the reason it's projective reps is because when you calculate observables in quantum mechanics, basically it's because it doesn't care about the phase of the wave function. You take the mod of something, and that gives you the observable. So that tells you that quantum states transform in projective reps. Now, we're not talking about states, we're talking about fields. But you can take that statement about states that transform in these projective reps, and you can deduce from that how fields, operators on those states can transform. And you almost end up with this postulate. I say almost because there are tricky things with things like continuous spin representations that I don't really understand and aren't realized physically, so I don't want to understand. Good. So for our purposes, we're just discussing classical fields, and we can just take this as a postulate motivated by what we know about quantum field theory. Just an aside, I don't want to get bogged down in this, but it's a fact that we're going to be that finite dimensional representations of a non-compact group cannot be unitary. Okay, so finite, so non-compact group implies that finite dimensional reps, other than a trivial one, are non-unitary. And sometimes this confuses people and trips them up because they think they hear the words non-unitary, and non-unitary sounds scary because quantum mechanics is unitary, but this isn't scary at all. The thing that's unitary about quantum mechanics is the representations of the states. We're not talking about quantum states, we're talking about fields. And fields always transform under non-unitary reps. There's no problem with that whatsoever. If the word non-unitary is, at first glance, slightly frightening to you, then let me just point out that that transformation law is a non-unitary representation of the orthogonal group. It's finite dimensional, or of the Lorentz group rather. It's finite dimensional, it's not compact, so lambda here is not a unitary matrix. So this itself is a non-unitary representation. No big deal. We do non-unitary representations all the time. Okay, so that's fine. Okay, so the physics postulate is that we should be thinking about fields which transform in these finite dimensional projective representations. Yeah.
we're talking about real matrices, that is just restricted from the geometry is, like what I want to say, orthogonal. Like, if it's a real matrix, then, and this does satisfy lambda transpose lambda equals 1, right?
Lambda transpose eta lambda equals eta.
Yes.
It's not the same as lambda transpose lambda equals 1. So if we were doing the compact orthogonal group, then this would be there would be unitary finite dimensional representations. Like the usual representations of the rotation group labeled by L and M are unitary finite dimensional reps. It's the fact that we have a time direction is changing that. So it's taking it's basically the generators that are associated to the time direction are anti-Hermitian. So the generators associated to the space directions are Hermitian, but the generators associated to time direction are anti-Hermitian. So overall, the matrix is non-unitary. Okay. So the answer to what is a field is that it's something that transforms under a projective rep of the restricted Lorentz group. So now we're supposed to use math to figure out what those reps are. And there's a fact you can look up in a math book, and I'll sort of explain, which is that finite dimensional projective reps of a Lie group G are in one-to-one correspondence with finite dimensional reps of the Lie algebra little g is corresponding to that group. Okay, so in this case, what that means is that after all that, what we're really supposed to do is just forget about the group and focus on the algebra. This is the fact that in physics we care about projective reps. Okay, so what physicists like to do is just to completely ignore the distinction between groups and algebras and uppercase and lowercase letters. But this is the reason for it. It's because physics is about, it's because the group transformations in the Lorentz group are projective reps, and those really do have a one-to-one correspondence to the representations of the algebra. So why is this the case? Well, it kind of makes, I'm not going to prove it, but it kind of makes sense. So let's go both directions. So if you have a representation of the group, then you can look at the infinitesimal transformations, and that gives you representations of the algebra. Okay, so that way is easy. Now if you try to go the other way, you have some representation of the algebra, you try to exponentiate and get a representation of the group. It's going to work locally, but it might fail globally. It might fail due to some global properties of the group. But the only way it can fail is by making it a projective rep instead of an ordinary rep. So, that makes sense? Basically, the projective reps say that we can ignore the global issues with exponentiating a representation. We're going to see examples of this with spinners, but that's the general idea. So what we really care about are representations of this Lie algebra, which I'll write for reference. M nu, M rho sigma is equal to eta mu rho, M sigma minus eta mu rho, m mu sigma minus eta mu sigma m mu rho plus eta mu sigma m mu rho. If you don't want to remember that formula, then you can just remember that it's the same as the differential operators d. I think there's a factor of 2 here, 2x mu d mu, which are just the usual, yeah, just the usual generators of the Lorentz transformations. Questions? So the conclusion is that we should focus on the algebra, but before we do that, I want to say a bit more about the group. Because it's fun, so I want to say a few things about spin groups. So we're going to talk about these projective reps of the Lorentz group, but projective reps of the Lorentz group are actual representations of a bigger group. That group is called the spin group. So the definition, for our purposes, is just that if you take an orthogonal group, the connected component of an orthogonal group, then it's locally identical to the spin group, but the spin group covers the orthogonal group twice. So in terms of rotations, this means that you unwrap a 2 pi rotation to a 4 pi rotation, and you consider, so basically you take 2 copies of the orthogonal group, and if you're between 0 and 2 pi, or you consider that one of the spin elements between 0 and 2 pi, and the other copy is the spin elements between 2 pi and 4 pi. Leo looks confused. Did I say something wrong?
No,
Okay.
so it doesn't do anything to time, right? It's just unwrapping this non-contractible cycle that you mentioned, or it's more complicated.
Certainly for the 1 comma d minus 1, I'm actually not sure how to define how to do this in the general one, which whether there's a choice of Z2s maybe. But certainly for the ones we're interested in, where m is 1, that's right. We're literally taking the rotation. It doesn't do anything with time. It takes the rotation and unwraps it. So there are some special examples where you already know about spin groups, even if you've never heard of a spin group. So, for example, you've all heard of spin 3. SU2. Right, so we know the statement from quantum mechanics that SO3 is double covered, has a double cover in SU2. So this is just a generalization of that. There are some other ones that are important. I'll just write down a couple of them, and you can store them away in your brain for later use. Spin 6 is, in the same sense, gives SU4. This is important for conformal field theories in 4 dimensions. Spin 1 comma 2. So this is the double cover of the 3-dimensional Lorentz group. Spin 1 comma 2 And the last one I'll mention is probably most important, and that's spin 1, 3. So this one is the double cover of our Lorentz group, the 4-dimensional Lorentz group. So this one is SL2C. And so remember at the beginning of the lecture, I mentioned that one of the great things about spinners was that it gives you good tricks for dealing with SO13. Well, what I really meant was good tricks for dealing with spin 13. And the reason there are good tricks is because it's secretly this 2x2 matrix group SL2C. So this one we're going to get to know in detail a little bit later, but I'm not going to talk about it now because I'm still in general dimensions, and that stuff's special to 4 dimensions.
Right. Is there another one that's like SL2 cross SL2 for SO4 or SO31? The one particle physicists use.
This one is I believe, isomorphic to SO22, which is isomorphic to SL2R times SL2R. I think these are all the same. I think all 4 of these are the same. Does anyone know if I made an error in saying that? I'm trying to be careful here, but I didn't have that one written down. I think that's good. It's certainly true if you complexify the algebras. Whether these are globally true, okay, let me erase it just in case anyone walks out and sees. So, not quite done with spin groups yet. I'm going to define a couple things. One is the universal cover. The universal cover of a manifold is, okay, I know this is not a very precise definition. You can look at Wall for the precise definition, but it's the manifold you get by unwrapping all of the cycles. So, for example, the manifold S1 is just phi identified mod 2 pi, and its universal cover is what you get if you just throw out the identification. So the universal cover of S1 is the real line. Similarly, the universal cover of a torus is just high dimensional, real line. Euclidean space. From the definition, it's clear that universal covers are always simply connected. They don't have any cycles. They don't have any non-trivial cycles. If they did, then you haven't finished yet. You have to keep unwrapping. So now I'm going to state 2 math theorems that clarify the relationship between algebras and groups and the representations. I just want to state them, have them on the board. You can look back at them when you get confused about all this stuff. So the first is that given a Lie algebra G, there's a unique, simply connected G group big G with the algebra little g. Okay, so groups and algebras are different things, but if you require the group to be simply connected, there's a one-to-one correspondence. There's precisely one simply connected group or algebra. And any other G prime with the same algebra must be some quotient of that simply connected. It's a quotient by a discrete central subgroup Z and G. So for example, the algebra SO1, 3 has different groups that have the same, that have that algebra. So we could take one of them to be this SO plus 1, 3 group, or restricted Lorentz group. We could take another one to be SL2C. And SL2C is the simply connected one. The restricted Lorentz group is the quotient of that. So G prime, in this case, is G mod C2. What this theorem means is that G prime, or rather G, is the universal cover of G prime. For D greater than or equal to 4, spin 1 comma D minus 1 is simply connected, and so is the universal cover of SO plus 1. D minus 1. So this is something that maybe you've seen the proof of this before, at least in pictures. Should I tell you the pictorial proof of this statement? Why a rotation by, so remember how we defined the spin group? We said that you take a double cover of the rotation. Okay, so to prove this, okay, put that in quotes, so we're doing theorems here. So the proof of this is the fact that a 4 pi rotation contracts to nothing. Okay, so this is a bit hard to picture, but there are some nice pictures actually in Wald, and I could show you how this works. Okay, so here's the idea. Take an object, and someone tells you, rotate that object by 4 pi. So the question is whether that procedure of rotating an object by 4 pi can be continuously deformed to the procedure where you do nothing at all. So here's how you do it. So first you split it into, you can view that as rotating by 2 pi plus 2 pi. So you have, this is the object, this is the axis of rotation. So you rotate it once, and then you rotate it again. And now we want to deform this procedure. And the way we're going to do it is we're going to take one of these rotations and deform it to the left. Okay, so we deform this. So it looks like this, where first we rotate by 2 pi around the z-axis, and then we rotate by 2 pi around that axis. So we're just deforming this procedure. We're doing it in a continuous, smooth way, and we're going to deform this other axis of rotation until it's all the way at the bottom. So first we rotate by 2 pi that direction, and once this one gets to the bottom, it's just going to be a rotation by minus 2 pi along the z-axis. And this is equal to the do nothing procedure, where you just don't move the object at all, because you've just rotated and rotated back. Notice that this procedure that I just described was the way, even just the way I drew it on the blackboard. This was a procedure that used 3 space dimensions. This object that I drew, I was drawing as a 3 space dimensional object. And this doesn't work in less than 3 space dimensions. So d less than or equal to 3. So for example, it turns out that the universal cover of SO plus 1 comma 2 is not the double cover, it's the infinite cover. So no matter how many times, if you have an object on a plane, 2-dimensional spatial plane, no matter how many times you rotate it, that's always a non-trivial operation that can't be deformed to the identity. Okay, so if you want to unwrap the cycle, it's not enough just to cover it twice. You have to cover it an infinite number of times, and so universal cover is just completely unwrapped to R3, covering the original manifold times. And in physics, this translates into the statement that spin in 2 space dimensions is a continuous label, not a half integer. It is the fact that they're anyons in 2. Okay, so let me conclude this aside with one more theorem, which I've more or less said now, but I want to state it in something precise, is that the reps of G are in one-to-one correspondence with the reps of little g, if and only if G is a simply connected group. So this is one of the fundamental theorems of Lie algebras or Lie groups. I think it's like one of Lie's theorems. Lie himself. So, going back to the physics situation, we summarize the situation as follows. Physics tells us that we should think about the reps of the algebra SO1 d minus 1, which are equivalent to the projected reps of the Lorentz group, which are equivalent to the actual reps of the spin group. Okay, this is a roundabout way of saying that physicists were right all along. You should just ignore the distinction between algebras and groups. It's not quite true. There are global properties of, we can't just ignore global things altogether, and we'll see that especially when we put things in curved space and talk about putting fermions on a manifold in topology. Okay, that's my aside. Now we're going to go back to physics. Are there any questions so far? Yeah.
Maybe the fact that you said there's anions in 2D, why do they take like the reps of 2D CFDs to have integer scales? Or is that just a choice?
2 plus 1 dimensional CFTs?
Yeah.
That's a good question. I suspect that you don't have to do that. There's probably a generalization where you don't do that. Any questions? Okay, so that was kind of abstract. Now we're going to get a little bit more concrete. We might go back and talk more about the various, about classifying representations of this algebra. Maybe not. Maybe that's too boring. But we're not going to do it now. We basically have formally answered this question of what is a field. It's something that transforms a representation of the Lie algebra. And now I just want to introduce Dirac spinners. We can easily check that they satisfy this postulate, and we can worry about the general case another day. So now for the Dirac spinner. In Minkowski. So my conventions until further notice are conventions of the book by Friedman and McBride. So the first step is to introduce the gamma matrices. Gamma is 2 eta, where gamma is an n by n matrix. N is equal to the bracket d over 2. So this is just how big you have to make it to get this to work. I don't want to go into the explicit construction of the gamma matrices because I think most people have seen it and it's kind of boring. But you may or may not have seen it in general dimensions. For now, we're still in d dimensions. And basically, when you go up from an even to an odd dimension, you don't have to increase the size of the gamma matrices. So that's where this bracket comes from. It says to take the integer part of d over 2. Let me introduce the spin matrix. The spin matrix sigma mu nu fourth commutator, gamma mu, which is also defined to be a half of gamma over mu nu. So the gamma with multiple indices is the anti-symmetrized product of gamma matrices. So that gives you one factor of 2, and then we wanted another one, so that's the factor. You can check, I'll call it an exercise, if this obeys the SO 1, D minus 1 algebra, that is this thing, the spin matrix sigma, obeys the algebra I wrote a few boards ago with all the m's in it. A good formula to know, if you want to check that, and just in general, is sigma mu nu gamma rho. The commutator, so you can think of this as the action of the Lorentz generator on a vector. And the action of the Lorentz generator on a vector has to have a very specific form, which it does. It comes out just right. That's gamma mu, eta mu rho, minus gamma nu, eta mu rho. So the upshot of the discussion that we just had for the last hour is that if we define objects transforming with this matrix, then those are going to be good physics objects, projected reps of lines. So those objects are called Dirac spinors. It's an n-component thing called psi. It transforms as psi, there's a psi prime, equals m of lambda psi, where m of lambda is e to the minus a half lambda rho sigma, big sigma rho sigma. All these generators have the n by n indices that act on components of the object sum. Okay, so the discussion we had says that this is a projective rep of SO plus 1 on the D minus 1. And with a little bit of work, you can show that it's not a genuine rep. As you know from spinors, they should transform by a sign when you rotate by 2 pi. So I know you already know that, but I just want to state it in the language that we've been presenting here. So in this language, the rotation by 2 pi in the 1-2 plane is what you get if you just set these real parameters, lambda 1, 2, to 2 pi. And if you find the associated, if you find the Lorentz matrix associated to that, so remember that's this e to the half lambda mu nu t mu nu. That Lorentz matrix is just the identity, because it's a rotation by 2 pi. But in the spinor representation, this matrix M is e to the 2 pi sigma 1, 2. With some effort, I'm not sure what the easiest way to do this is. One way to do it is to plug in, is to look up the gamma matrices and plug them in into the matrix exponential. If you do this rotation, you get minus the identity acting on the spinor components. So, in other words, if we think of this if you hand me a group element in the Lorentz group, and I turn that into one of these spinor transformation matrices, this map is ambiguous. It's perfectly well defined in terms of little lambda. You just exponentiate the generators. But if you hand me the same group element, that is the identity and the identity after going around once, you get two different generators acting on the spinors. So this is a double valued, it's a double valued function of the group element. It's ambiguous up to a sign. If you want to specify it uniquely, you have to tell me not only the group element, but how you got there. So that was a Dirac spinor. A Dirac field is just a spinor at every point in space-time. So we just give it a label x, and we say that psi of x transforms to psi prime of x prime equals m of lambda psi of x. And for now, that's all I have to say about spinors in Minkowski space. So, or about Dirac spinors in Minkowski space. Now, so this is the lightning review of hopefully something that you've seen if you've taken quantum field theory to define Fermi. The goal next is to understand how to take these objects and incorporate them into everything we did so far this year, into general relativity. So this is not trivial. There's some deep reasons for why this is not trivial. So if we want to put psi in space-time, at an operational level, the reason, or one of the reasons that this is hard, is because there's no analog of the tensor transformation rule that says d prime alpha is equal to d x prime alpha dx beta d beta. Now this is how we said tensors, this is how we define tensors. We said they transform this way under general coordinate transformations. Now for spinors, we've understood in Minkowski how they transform under the Minkowski isometries. But it's just impossible to write a formula like this for spinors. It can't be done. So this was the general coordinate. And I'll try to explain probably next time why that's possible. Since I only have 3 minutes left, maybe I'll just give the strategy for what we're gonna do instead. We can get into the details next time, but if there are questions, I can answer those. Okay, so here's the strategy. The idea is to introduce, at each point in space-time, so at a given point x in space-time, we're going to introduce a local Lorentz frame. Now this is something we could have done for tensors too, and we'll start by doing this for tensors. So this is called the Vielbein or tetrad formalism. It's occasionally useful for non-spinor fields. Actually, at least in anything I've done, I don't remember ever finding this useful for tensors. I can't think of a time. For spinors, it's not optional. So for spinors, because of this issue that I just mentioned, you don't have a choice. You have to introduce local Lorentz frame. You have to introduce local Lorentz frames at each point in space-time. And once we've done that, we can deal with spinor fields by just declaring that they transform. So we already understood spinors in Minkowski, so in special relativity. So what we're going to do is we're going to introduce local Lorentz frames and declare that spinors act under local Lorentz transformations just like they did in special relativity. This is going to turn out to be, it's not obvious from the way I'm saying that this is enough. What do we mean by enough? Well, we need to be able to, if we want to incorporate these into GR and do fermions in curved space, at the very least, we need to be able to define a covariant derivative. Without a rule like this, you can't define a covariant derivative in the usual way. But introducing these local Lorentz frames will allow us to define a covariant derivative that works in the usual way, and then we can start writing laws for fermions in curved space. Okay, so that's the plan. And if there are no questions, I guess we're done. I'm not going to spend 30 seconds doing this. Oh, no lecture Thursday. I told you that already, but again, no lecture